We'll go to the next subtopic, which is overheads and pointers. The functions of overheads are to implement layered monitoring management for SDH signals. The monitoring is classified into the section layer monitoring and the path layer monitoring. The section layer monitoring is further classified into the regenerator section overhead and the multiplex section overhead or MSOH. While the path layer monitoring is further classified into the higher order path overhead and the lower order path overhead. And the layered monitoring for SDMN is implemented. The overhead of each layer, including RSOH, MSOH, HPOH, and LPOH, consists of some different bytes for different OEM function. As several overhead bytes, for example, the K1 and the K2 bytes, are very important for maintenance and troubleshooting. According to ITUT recommendation, there are some overhead bytes reserved for national use. The A1 and A2 bytes. Like a pointer, the function of the frame byte is alignment. The first step is to properly extract each SDMN frame from the received continuous signal stream at the receiver. The function of the bytes A1 and A2 is to locate the start of the SDMN frame. So the receiver can align and extract the SDMN frame from the information stream via these two bytes and further align a specific low rate signal within the frame via the pointers. If the receiver doesn't receive the A1 and A2 bytes within 5 or more successive frames, it will enter out of frame status and generate out of frame alarm or OOF. If the OOF keeps for 3 milliseconds, the receiver will enter loss of frame status. The equipment will then generate loss of frame alarm or LOF. Meanwhile, an AIS signal will be sent downward and the entire services will be interrupted. Under the loss of frame status, if the receiver stays in normal frame alignment status again for successive 1 millisecond or more, the equipment will restore the normal status. D1 to D12 bytes. The data used for OEM functions such as send commands and check alarm performance data are transmitted via D1, D12 bytes within the SDMN frame. Therefore, the D1 to D12 bytes provides a common data communication channel accessible to all SDH network elements. As the physical layer of the embedded control channel or ECC, the D1, D12 bytes transmit the OEM function among the network elements and form a transmission channel of the SDH management network or SMN. E1 and E2 bytes. E1 here is part of the RSOH and may be accessed at regenerators. And E2 is part of the MSOH and can be accessed at multiplex section terminations. Each of these 2 bytes, it provides a 64 kilobit per second order wire channel for voice communication. The order wire provides a convenient communication function during maintenance and troubleshooting. The B1 byte is allocated for regenerator section error monitoring. The byte B1 is located in the regenerator section overhead. The bit interleave parity code or BIP8 byte, it is a parity code or even parity, and it is used to check the transmission errors over the RS. The B1 BBE is represented by RS BBE for performance event. B2 byte. B2 is similar to B1 in operation mechanism except that it monitors the error status of the multiplex section layer. The bit interleave parity code MS-BIP24, it is used to check the bit errors over the MS. And the B2 BBE is represented by MS-BBE for performance events. And also the working mechanism of B2 is same as B1. The M1 byte. If the B2 at the receive end has detected an error blocks, the number of error blocks detected by the B2 will be displayed in this end performance event MSBBE. At the same time, M1 will be used to report to the transmit end that error blocks have been detected, and the transmit end will report the MSFEBBE performance event and the MSREI alarm. The M1 is a message written to its transmit end by the receive end so that the transmit end can get the receiving error status of the receive end. For STM-N levels, this byte conveys the count of interleaved bit blocks that have been detected in error by the BIP24. The K1 and K2 bytes. The 2 bytes are allocated for APS signaling for the protection of the multiplex section. This is an alarm message. It returned to the transmit end or source by the receive end or sink, which means that the receive end has detected an incoming section defect or receiving the MSAIS. That is, when the receive end detects receiving defects, it will return an MSRDI alarm signal to the transmit end so that the latter obtains the status of the former. If the received B6 to B8 bits of the K2 is 110, it means that this signal is an MSRDI alarm signal returned to the opposite end. If the received B6 to B8 bits of the K2 is 111, it means that the signal is an MSAIS alarm signal received by the current end. The S1 byte. We can use the extended SSB for clock protection. In this case, the different value of bits 1 to bit 4 of byte S1 indicates the different clock source. For bits 5 to bits 8 of byte S1 allocated for synchronization status messages. This table, it shows the assignment of bit patterns to the 4 synchronization levels agreed to within ITUT. The 2 additional bit patterns are assigned, one to indicate that quality of the synchronization is unknown, and the other is to signal that the section should not be the synchronization. The remaining codes are reserved for quality levels defined by individual administrators. Path overheads. The section overhead is responsible for section layer OAM functions, while the path overhead for path layer OAM function. J1 byte. It is the start of the VC4, so the AU pointer indicates the location of the J1 byte. The default transmit and receive J1 byte values of the equipments provided by Huawei company are the Huawei SBS. Of course, the J1 byte can be configured and modified according to the requirement. The received J1 should match or be the same with the expected J1. The B3 byte is allocated for monitoring the transmission error performance of VC4. Its monitoring mechanism is similar to that of the B1 and B2, except that it is used to process BIP8 parity and the VC4 frame. The C2 byte is allocated to indicate the composition of multiplexing structure and information payload of the VC frame. It is such as equipped or unequipped status of the path, the type of loaded services, and their mapping method. To configure the multiplexing of 2 megabit per second signals for Huawei equipment, the C2 is required to be configured as TUG structure. The received C2 should match or be the same with the expected C2. If not, the HP SLM alarm will be generated, which interrupts the service within VC4. The LPOH here, or low order path overhead, it refers to the path overhead of the VC12 that monitors the transmission performance of the VC12 path level. The lower order POH is located in the first byte of each VC12 basic frame. An LPPOH consists of 4 bytes, which is denoted as V5, J2, N2, and K4. Usually, the V5 byte is the most important in LPOH. The V5 provides the function of error checking, signal label, and path status of the VC12 path. So this byte has the function of the G1, B3 and C2 bytes within the higher order path overhead. The function of the pointers is aligning via which the receiver can properly extract the corresponding VC from the STMN and then disassemble the VC and C packages and extracts the lower rate PDH signals. The TU pointer and the AU pointer, it provides a method of allowing flexible and dynamic alignment of the VC within the TU or AU frame because these two pointers are able to accommodate differences not only in the phases of the VC and the SDH but also in the frame rates. The AU pointer, it is located in row 4 in column 1 to 9. This is within the STM1 frame. It is used to indicate the specific location of the first byte J1 of the VC4 within the AU4 payload, so that the receiver can properly extract the VC4. The AU4 pointer provides a method of allowing flexible and dynamic alignment of the VC4 within the AU4 frame. The TU pointer is used to indicate the specific location of the first byte V5 of the VC12 within the TU12 payload. It is so that the receiver can properly extract the VC12. The TU pointer provides a method of allowing flexible and dynamic alignment of the VC12 within the TU12 multi-frame. The TU pointer is located in the bytes denoted as V1, V2, V3 and V4 within the TU12 multi-frame, and the TU pointer of the TU3 consists of H1, H2 and H3. Their function is similar to that of AU pointer. In summary, we have already learned for SDH overview the frame structure and multiplexing methods and also the overheads and pointers. The focus is the mechanism for the bytes to monitor alarms and performance. Thanks for watching.